Well, I hope you had a great holiday and that you caught up on everything that we have taken thus far. We're going to start up with titrations right now, and especially different titration curves of neutralizing an acid or neutralizing a base. And then we're also going to look at diprotics in the next follow-up recording. For now, what is a titration? In a titration, a solution is of an accurately known concentration is added gradually to another solution of an unknown concentration until the chemical reaction between the solutions is complete. And actually, a titration was an analytical technique generally used to find the unknown concentration of a certain material. And we neutralize the amount of that material as we add a base, let's say, to an acid. We do a neutralization reaction. In an endpoint, the endpoint is the point at which the reaction is complete. Once I'm done with the first neutralization and the reaction has been completed, that is my endpoint for that particular reaction. There's a difference between endpoint and equivalence point. The equivalence point is a single point in which the amount of moles of H3O plus in my solution is equal to the amount of moles of OH minus. Or if it's not a strong acid, if it's a weak, the amount of moles of a weak acid is equal to the moles of the base used to neutralize that acid, which is usually a strong base. An indicator is a substance that changes color at or near the equivalence point. Now you have to watch out. We're going to look at these indicators in a separate chapter briefly at the end of this, but I'm going to show you the different types of indicators and what do we mean by at or near the equivalence. So what are the equipment that I need to use to do a proper titration? Well, I need a burette, which is a column-like glassware where there's volumes here, where you could read out the exact volume that you're adding once you open the stopcock. And then here you have a Erlenmeyer flask, which you have your unknown usually in the Erlenmeyer. Now we start adding what is called the titrant from the burette, that is the known material, to the unknown, which is also called the analyte, which is usually in my flask or Erlenmeyer flask. And I usually also need an indicator, few drops of that indicator, and a water bottle, such that every time I do the addition, I do a little bit of washing and if I add a few drops of the indicator. Now I keep adding the titrant to the analyte up until the indicator changes color. Upon the change in color, that tells me that I have reached my equivalence point, where the moles of H3O plus equals to the moles of OH minus. And this is how we actually hold our apparatus. We use one hand in order to do a swirl-like to my Erlenmeyer flask, and we use my left hand to open up the stopcock. And my known is normally my titrant in my burette, and I slowly add drop-wise, opening up the stopcock to my unknown analyte in the flask. Okay, now the analyte amount, before I do that, the analyte amount is usually in milliliters, and it's usually added in a pipette in an exact volume, but the concentration is generally unknown in some cases. Now, in other cases, we actually know the concentration and we want to find the pH, which we're going to see in a moment. So at the beginning of a titration, here we are, we have H plus or a strong acid in my flask, and I have OH minus in my burette, and I dropwise add the OH minus or per milliliter amounts. I keep adding the OH minus until there is a color change. Now the color change might appear at some point in my titration, but upon swirling, that color actually gets removed. And it's only when the color change persists in my flask, that's when the end point has really, the equivalence point has been reached. Nonetheless, I don't have to just do this until I get the equivalence point. I could actually follow up each addition, volumetric addition, using a pH meter and not just using an indicator. What do I mean by that? I mean that I hook now to my beaker. In this case, here's a beaker. It's usually better off. In this case, you're going to have a swirler or a spin vane and something swirling. And I attach my analyte solution with a pH meter and then pH electrode. Now, once my electrode is in, every time I dropwise add the OH minus to my HCl inside my beaker, the pH will change. Of course, the pH will be low initially due to the only acid in my solution, and then the pH will start to increase as I add more and more OH minus. Now we monitor this pH change as a function of the volume of added OH minus. Another way to do a certain plot is to plot the pH as a function of a variable which we call x. This variable x is actually a ratio of the volume added to the volume at the equivalence point. It's pretty much the same shape of curve, just a difference in the x on the denominator. Difference in the, here we have an example of a pH curve. So this is a titration curve of a strong acid, HCl, titrated with my titrant strong base, OH minus. And so what we have here is the volume on my X versus Y for the X-axis, Y-axis. My X-axis here is the volume of OH minus, or NaOH, and my Y-axis is the pH. And so such a titration of a strong base, NaOH, with a strong acid, HCl, the net is OH minus plus H plus or H3O plus is going to give us O or 2H2O liquid. Now let's look at this curve briefly. How can I tell what the equivalence point is and where is the equivalence point? Well, the equivalence point occurs at the major change in pH value. So if you look at this curve, there's a gradual increase in pH. Let's say here it's going from pH 1 to slowly go down. Let's look at it. pH 1, 1.18, after 10 milliliters is 1.37. Look here, even after 22 milliliters, it's only 2.2. So there's a gradual increase in pH. And then suddenly, look at volume 24 milliliters of NaOH added, the pH is 2.69. So from 0 to 24 mils, which is right there, the volume, the pH mildly changed. Then suddenly, a sharp, huge increase with 1 milliliter value difference from 24 to 25, a sudden jump to pH 7, and then another jump again with another milliliter difference from pH 7 to pH approximately 11 point something. So look at the sharp increase. It's at this volume where you find a sharp increase in pH, that's my volume of at equivalence point. And you could extrapolate the volume. Where would that be? Anywhere across this area. Now, to be exact or more exact, you would do the parallel tangent. So you take two parallel lines on the tangent where the curvature starts to increase, and you would take the half midpoint of the perpendicular line between those two parallel lines. So we take the midpoint between that, and then you do another parallel, and that would give you the exact, or an extrapolated equivalence point pH value, as well as a volume at equivalence. Nonetheless, for pH, for strong acid with a strong base titration, the pH at the equivalence point is always equal to 7. Okay, at the same time, you could always have indicators inside your solution. I could have, for strong acid, strong base, I could use either, for example, methyl red, or I could use phenolphthalein. How do I know that I could use those indicators? Well, if the change in the indicator color occurs anywhere within the region of the sharp increase in pH value, okay? So if you look at this volumetric, so this is volume at equivalence, and notice either the methyl red indicator or the phenolphthalein have a change in color in the range where that line, that sharp increase line, volume, is taking place. You're going to see this a little bit in a moment, see the difference with other titration curves. Okay, so what are some features, again, of this strong acid, strong base titration? So first of all, like we said, the pH starts low and increases gradually, and then there's a sudden sharp rise, okay? And this occurs in the vicinity of the equivalence point. For this type, the pH at the equivalence is always equal to 7, and beyond this step, the pH increases slowly, okay, as more and more base is added. Okay, let's look at now if I wanted to do an actual calculation of the pH. Well, there are mainly really 3 regions, if you will. The first region is my initial pH value, okay? And the initial pH, is whatever I have in my beaker or in my flask. So if I started with H3O plus, or the strong acid in my flask, my initial pH would be the pH of that strong acid. As I add more OH minus, before the equivalence, so anytime I'm before the equivalence point, I always have more H3O plus than I have added OH minus. At the equivalence point, I have equal amount of H3O plus as OH minus, which means they both cancel each other out in terms of the number of moles. Thus, I only have water. Thus, my pH is equal to 7. After the equivalence point, that's when the OH minus starts to become in excess. First, you have to find the volume at equivalence point. How do we do that? We say CAVA equals CBVB. So number of moles of the acid equals to the number of moles of the base at the equivalence. Okay? And then we can find the volume of base needed to neutralize a certain amount of acid. So this is an example where I have already a known concentration of acid and a known concentration of base, and I'm changing the volume of base from the burette. So I could always get the volume first at the equivalence point. And now let's look at any point before equivalence. Before equivalence, the concentration of H3O plus is greater than OH minus. So let's set up a chart where I have a reaction between H3O plus and OH minus giving me 2 water. Of course, this is a complete reaction because the K reaction for this one is just 1 divided by KW because the opposite is KW. Okay, so initial millimoles, and the reason I say millimoles is because my initial millimoles, and the reason I said millimoles because I'm going to put my volume in milliliters. Now you could use moles by putting a volume in liters, that's up to you. So that's the concentration of H3O plus concentration times its volume. And here I'm going to put the concentration of base times the volume of base that has been added. And now we have a known volume of base added. Of course, if I'm before equivalence point, my base is my limiting reactant. So there's gonna be less base than acid. So that amount is gonna tend to 0 or epsilon. And I'm gonna subtract the limiting from my excess reagent. So my excess CAVA minus CBVB. Of course, water is always in excess, so we don't put a concentration for it. What's my pH? The pH will be whatever I have in my solution. What do I have in my solution? I only have H3O plus. And therefore my pH will be the minus log of H3O plus concentration in my solution. Well, don't forget, this is not concentration, this is millimoles. If I divided that by the total volume in milliliters, which is the volume of the acid plus the volume of the base in total, that's the concentration of acid in my solution. Okay, and that will give you your pH. Now, at the equivalence point, of course, I don't really have to write an equation because CAVA equals CBVB, and therefore they're both equal in amounts, the H3O plus and OH minus, and therefore this would tend to epsilon or 0, OH would tend to 0, I only get water, so my pH is 7. After the equivalence point, the volume added, after the equivalence point, that means that my OH minus is in higher concentration than H3O plus. And if you go back to your millimole chart with CAVA and CBVB, and you're using the same amount that you had initially, whatever you had, of acid, but now my volume of base has changed and the volume of base now is greater than V equivalence. So the amount of moles overall of OH minus will be bigger. So this amount here will be in excess. And thus my H3O plus is limited and it's going to tend to 0. What am I left with in solution is only OH minus, with the number of moles in my solution is CBVB minus CAVA. What's the pH? Well, I get the POH first, and of course you all know how to get pH from there. Get the POH is the minus log of the OH minus concentration. What's the OH minus concentration? Well, it's the number of moles divided by total volume. Don't forget to divide by the total volume, guys. A lot of you tend to do that. You forget the total volume. And of course, once you get the POH, you get the pH of your solution, and you could do you can do a graph of this, or if they asked you at a particular volume, you can get every single pH. What I recommend for you to do is go back to this type of equation right here. And this is a 40 milliliter of 0.1 molar HCl titrated with the titrant NaOH of different volumes, and the concentration of NaOH is 0.1 molar. I have different pH ranges at different volumes. Choose some 2 volumes before equivalence, 2 volumes after equivalence. Choose like the half equivalence, what we call half equivalence. If the equivalence point is 40, half of that will be 20. It's always a good value to choose. Here it doesn't really make a difference, but you'll see why a little bit later on. I would recommend you do that. See if you can get these actual pH numbers, because in the problem set, there is no exercise for strong acid with a strong base in the problem set. Now, if we do now a titration oppositely, if now I have inside my beaker or my analyte is OH minus and my titrant is a strong acid HCl, then my x-axis will be the volume of HCl added, and my y-axis here will be my pH change. So we're going to monitor now the pH change as I add a different volume of HCl to some OH minus. Well, here's an exercise of some 50 milliliters of Na 0.5 molar NaOH with 1 milliliter HCl. And this is a type of curve which was, sought with such an amount. And this is the shape of curve that you're always going to get with a strong base titrated with a strong acid. Again, now here we start off with a high pH, not a low pH, because we have a strong acid initially. And we gradually have a decrease in the pH value. Look, you're going, let's say, from 13 down to like 12, down to 10. But then suddenly, whew, sharp decrease in the pH up until, again, equivalence point, pH 7, and then another sharp decrease in pH. So you get a sharp overall decrease in pH all the way down to close to pH 2. Okay, and that's when we start to have, after the equivalence point, some excess of acid. So initially we have excess base in this area, then we have only water at the equivalence point, and then we have excess of acid after the equivalence point. All right. Okay, so if we look at this, titration of a strong base, with a titrant being the acid, we also see that the indicators used are pretty much possibly phenolphthalein and phenyl red indicator. Now, what about this idea of indicators used? Again, if the change in color of the indicator, where we have different ranges of indicators, there are many, many indicators which I can use. So let's say, look at this, crystal violet, the change in the indicator color occurs between 0 and 2, and we're going to talk about this change in indicator color a little bit later. But I want you to concentrate again on where does this change occur. So if I have my pH at equivalence is 7, okay, in this example, what I want you to do is go to pH 7 here, and then go to plus pKa, okay, choose any indicator in the range plus or minus 1 of the pH at the equivalence point, okay? So take that, so this would be like methyl red, look at 6, so that's plus, and that's a minus pH minus 1, and this is a pH plus 8, that's, phenyl red or phenolphthalein. Any of these between 6 and 8 can be used as indicators, and usually the best indicator is an indicator which you choose with a pKa of the indicator. Either if you take the pKa minus 1 or the pKa plus 1 of the indicator, you will see that the P at the equivalence of your solution is within that range between pKa minus 1 and pKa plus 1. If it's within that range, then you could choose that indicator. Or if that indicator changes its color at the volume of the equivalence point, then you're also okay. And in the graphically, it's by far easiest to see if it's within this sharp change in pH, then you can use that indicator. Okay, weak. acid-weak base titration? Well, this is what the curve looks like for a titration of acetic acid with the titrant OH minus. So we have acetic acid with OH minus. Of course, as I add OH minus, I'm going to deprotonate the acetic acid to become the acetate ion and neutralize the OH into water. Now, initially, I only have what? As an initial, I only have H3O plus, the HA, or only the acid. As I add OH minus, my OH minus would be my limiting reactant. And as the reaction proceeds, it runs out. It's going to be limiting. It's going to become 0. And then I'm going to be left over with, in this area here, we call this a buffer region because it's a region where I have an existent amount of some leftover acetic acid with produced acetate or A minus. So this area here is an area where I have HA and A minus inside my solution after completion of the reaction. At equivalence point, that's when all of my acetic acid is neutralized with my OH minus, such that the concentration times the volume of this acid is going to equal to the concentration times the volume of this base. And when they're equal, they both run out in solution, they become to 0, and all of the acetic acid becomes acetate ion. So this becomes CaVa as a concentration. That's at equivalence point. So at equivalence point, I only have A minus. After equivalence, that's when I start to have more A minus as well as more, well, I can't have more A minus than I have acid, all right? So my limiting amount of A minus is the amount of acid moles, but I have more concentration of OH minus in my solution. Now let's look at the shape of this curve slightly, and we will distinguish it from the acid, from the strong. Well, here I also have a, more or less mild change in pH, but not as mild as the strong acid. Look, I'm going from pH 2, and after 24 milliliters, I suddenly jump to pH 6. So it's more of a gradual up change in the pH. Okay, much more than strong acids. And then I also have pretty much an increase, and yes, it is a sharp increase overall, but again, not as sharp. So I go from, let's say, from 24 milliliters, it's pH 6, to 26 milliliters. So 2 milliliters, I jump 4 pH units. So this increase is not as sharp as we would have seen in the strong acids. As well, well, those are the two major differences, really. Okay, so we have this buffer region again, which we never had in the area which we call in the strong acids. And again, why do we call it buffer region? If you look here from 0, pH 0, initial, but going from pH 5 to pH, to added 20 milliliters, there isn't that much difference in pH there, okay? There's more or less an initiation point, up initiation, but then suddenly I have a region here where there's hardly any difference in pH value. Okay, so here I have, what I want you guys to do is definitely memorize how this chart, and that is what is present in each point. Initially, I only have weak acid. So what is the pH of a weak acid? Well, of course, you all already know. Now, if the concentration of my acid is greater than 100 Ka, I'm allowed to use the following equation: pH equals half pKa minus half log HA. But if it's not, what do you have to use? Yes, you have to use the quadratic if it's not. So that's my initial pH. What if now my volume, okay, is in this region before the equivalence point. Now, before the equivalence point, I've actually divided it up into 3 regions, though I don't really have to because we pretty much use the same thing. We call this before the equivalence point. Everything is called more or less a buffer region. Why did I divide it into 3 points? There's no particular reason, but there's an area where the concentration of HA, the acid, is greater than A minus. But nonetheless, I still have this area where I have both HA and A minus. So what if I have that, what do I use? Of course, if you have HA and A minus, you always use Henderson. Of course, you all know that. So I'm going to use Henderson. pH equals pK plus log of A minus divided by HA. Yeah, sure, HA is greater than A minus, but still I'm allowed to use Henderson. Guys don't really get into when can we use it, when can we not. Like we said, as long as you have HA and A minus in solution, just use Henderson. In a buffer region as well, if my HA and A minus are equal, what happens to this value? The log, remember? Log of HA divided by log of A minus divided by HA becomes 1. And so pH equals pKa. We call this volume the equivalence divided by 2. So whenever my pH equals to my pKa, that is my half equivalence. So if my equivalence point was, say, 40 milliliters, at 20 mils, this is a point which I could right away put on pH equals pKa without actually doing any calculation. And when you're drawing the curve, you go upwards like this, a concave up, and then you switch concavity. In this case, you start, going like this, or sorry, this is concave down, and then switching the concavity slightly after that. Again, we're still before equivalence point. This is when HA is starting to become less than A minus. So I have now more A minus being produced, but I still am before equivalence. I still use Henderson because I have both in my solution, and we get a pH value. At equivalence, what happens at equivalence, guys, is all of my acid runs out. I get no more acid in my solution. All of it gets converted to A minus. So at equivalence here, my only substance is actually A minus. And so what is A minus to you, all of you? Of course, what is A minus? It's a base. Yes, it's a base. What is the pH of a base? What is the pH of a base? Well, you can get pOH of a base, or you could use this equation. Like I said, it does come in handy. The pH of a base is 7 plus half pKa of the acid of the base plus half log A minus, or you have to use the quadratic equation with a base Kb. But of course, what is the concentration of my base? Watch out for dilution because we have added dilution. It's not exactly the same concentration of my acid that I had initially because I added NaOH. So there's a dilution value. When can you use this equation? I should add that here. I can use this equation when the concentration of my base is greater than 100 Kb. Yes. Okay. After equivalence, what happens after the equivalence, guys? Well, I have some A minus, of course, inside my solution, but I also have some added OH minus left over after neutralization. And so I have a mixtures of 2 bases where I have a strong base and a weak base. And when we have mixtures of bases, we take the stronger base. And so the pH becomes, you just get the pOH is minus log OH minus in excess and get the pH from that. Make sure you know how to apply this chart, and we are going to use it right away. Please, right after this, stop and go ahead and do number 48. Please go right away and do number 48 in the problem set. Okay, stop listening to me and go do number 48. And finally, okay. So remember when we talked a little bit about the difference in the titration curve between a strong and a weak. So here's some strong in dotted lines. So you notice there's a much sharper increase in pH if it were a strong acid. In a weak acid, there isn't that sharp of a pH change. There is a sharp change, but not as sharp interval. The interval is smaller. Also, remember how in strong acids, I was able to use phenolphthalein and methyl red because both phenolphthalein and methyl red for strong acids were in the region of the volume at the equivalence point. Now, however, in this case, phenolphthalein may be used because its changing color is within the region of the equivalence point increase. However, my methyl red is actually in my buffer region in the form of its color change occurs between, let's say, 4.5 and 6.5. So it's more in the buffer region and it's not in the area where I have an increase, a sharp increase. So I can no longer use methyl red, but I can still use phenolphthalein as an indicator. Also, the pH at equivalence. Let's look at the pH at equivalence for weak acids. You always get a pH greater than 7. So the pH for a titration of a weak acid is greater than 7. Tell me why. Why would it be greater than 7? The reason it would be greater than 7 is because at equivalence point, what species do I have? Yes, you have a weak base. You always have the A- species, which is a weak base. So the pH is greater than 7. Okay, and don't forget that here we have a buffer region, while in the strong acid, there's nothing called a buffer region. We also don't care about the half equivalence in the strong acid titration, but we do care about the half equivalence point in the weak acid titration because that half equivalence point is simply equal to pKa of the acid, which depending on what the acid is, you could right away get that point without doing any calculation. All right. Now, what about this increase? There's an idea here that states that as my Ka decreases, in other words, as my weak acid becomes weaker, this increase margin becomes narrower. So you start having a narrower increase in the pH. So there isn't much of as my Ka increases, as you have a higher Ka, you have a larger, so it's more acidic, you have a larger region where you have a sharper increase in pH. Okay, and there's also, as my Ka becomes smaller, the pH at the equivalence point becomes higher and higher. And now for the idea of predominance. Remember how I told you I'm not going to talk about predominance till I start talking about titration. Well, after each titration of a species type, I'm going to talk about the predominance. So for example, now we're talking about the titration of a weak acid HA. And we just saw the titration curve of this weak acid HA, and we saw how this HA became A-, and we said that there's a point where HA equals to A-, and that's the half equivalence point, and that's the pKa value for it. Well, we can also look at this as I'm increasing my pH, as I become more and more basic by adding OH minus, I'm going from a certain amount of HA and I'm adding more A minus species in my solution. And this is actually governed by Henderson. So in Henderson, the minute I add 1 drop of OH minus, I have produced some A minus in solution. So the change here is really governed by a Henderson equation, because I'm going to end up having, no matter how small, some amount of A minus with some amount of HA in solution. So let's look at some variance. When the pH equals pKa, what happens here? Remember, when pH equals pKa, that means my A minus is equal to my HA, because let these guys be equal. That ends up becoming 0. Log to a 0 is equal to 1, and so my A minus equals to HA. What if my pH is greater than my Ka? So this here, I'm looking at this area where my pH is greater than my pKa. So pH is greater. As my pH is greater, that means take the pKa to the other side. This becomes a positive number, because a larger number minus a smaller number is a positive. Log 10 to a positive number is greater than 10, right? Positive 1, positive 2, positive 0.5. So it's greater than A minus will be greater than the HA. So that's an area where A minus is greater than HA. If my pH is less than pKa, then pH minus pKa is negative, so that's 10 to a negative number. That will tell me that my A minus will be less than HA. So when I'm becoming more acidic, I have more HA, more basic, more A minus. And my pKa is my midpoint, where I have equal amounts of HA and A minus. So here is actually the species diagram, where I have initially at the beginning, and this is variation with pH. At the beginning, I only have HA of a low pH value. And as my HA decreases, as I'm doing a titration, for example, as I'm adding pH and titrating it with OH minus, my HA decreases while my A minus species starts to increase. Up until what? Up until I get 50-50 amounts, equal amounts of HA and A minus. That's 50% of my solution is HA, 50% is A minus. This is what? This is when the pH equals to my pKa, absolutely. And then I go up higher, A minus is increasing while HA is decreasing. What is this pKa minus 1, pKa plus 1? This is when I have 90% of my species is HA, and I get 10% A minus. And in here, I have 90% of my species is A minus, and only 10% of it is HA. And so this is also the real predominance. In other words, this is where A minus predominates, and really predominates as in only it exists, you know, HA is less than 1/10 or of the A minus concentration. Now you don't have to worry about this part at this point. What you have to know is you put the pKa value, and then the species that dominates before the pKa, okay, at a lower pH than the pKa is A minus, and the species that predominates after pKa, is HA. After pKa, it's A minus. Okay, so this is the same type of curve for acetic acid. So here is my acetic acid. Its concentration is decreasing as my acetate concentration is increasing. At pH equal to pKa, we have 50% of my species exists in the acetic acid form and 50% of it in the acetate ion form. So this is what you have to put in. At pH increases, as pH increases, at pH equals to pKa value, I have the species are equal in amounts. At pH less than pKa value, my acid is more than my base. And as my pH is greater than pKa, my base form is greater than my here. All right. Okay, so please make sure again to do number 48, please. Number 40. Now the next is the titration of a weak base with a strong acid. Okay, so now we're titrating a weak base with a strong acid. The weak base in this case is ammonia, so it's a neutral weak base. We're titrating with HCl, so in other words, again, HCl is simply H3O plus in my solution. And of course, as my ammonia reacts with H3O plus, it picks up a proton from that acid, it becomes ammonium plus and water. The equivalence point of such a titration will be less than 7, and the reason is because when all of my base ammonia is neutralized with my acid, so I have 0, 0 in my solution after the reaction is complete, then all of my ammonia has been converted to ammonium. So really net at equivalence, I have ammonium in my solution. Just looking at the shape of the curve, this is opposite to a weak acid. This here, we start with a high pH. We go gradually. Again, there's a inflection-like point here. It's not a straight line, so it's just a little bit of an decrease, sorry, in pH here. And then you change in the inflection point at half equivalence, and then you start going down till you reach equivalence point, and you become more and more acidic, and the pH decreases because you started with a base and you're going to add more and more acid form of that base, which is the ammonium. And that's just the shape of a weak base. And if you look at it in terms, again, there isn't that much of a sharp decrease in pH as you would have seen with a strong base titration with a strong acid. Again, this is your net take-home chart where you're going to calculate the pH of this. How do we get the pH? As I add a certain amount of HCl. So we have a weak base initially, that's my initial point. So initially I only have base in my solution. So what's the pH of a base? Well, we can calculate it with this equation, 7. On purpose, I used another equation. Remember, the POH equals half pKb minus half log B0. Or of course, you could also use pH equals 7 plus pKa plus half log B0. Okay, so here, of course, that's if the concentration of this base is greater than 100 kb, and if it's not, you have to use the quadratic equation. So it's just a weak base alone. Now, in the region before equivalence, so again, this is divided into 3 different parts, though overall, before equivalence, what do I have? I have also what is called a buffer region. Why do I have a buffer region? Because again, in this area, even if I put 1 drop of HCl, I have created ammonium with ammonia. So I have both the ammonium and the ammonia, and therefore I have the BH plus and B, and so I have a weak acid and its conjugate, or base and its conjugate acid. This is Henderson, which you will use. You use it all the way through the buffer region. There's an area here, of course, when the base is equal to BH plus, and that's the half equivalence. That's when the pH equals the pKa. At equivalence, what have we done? At equivalence, all of my ammonia becomes BH ammonium or BH plus. Okay, so my base, my neutral base becomes BH plus. And what is BH plus? It's just a weak acid. So if that weak acid concentration is greater than 100 Ka, do not watch out for dilution. So watch it. Make sure you have the correct concentration of BH plus in your solution. This is not the initial. Anyways, you didn't have anything initial. course, you use a weak acid pH equals half pKa minus half log B0, or you actually, after dilution, you may have to use the quadratic. That depends. Mixtures of two acids is after equivalence point. So after my equivalence here, I have now more added H plus from the acetic acid than I have produced of the weak acid BH plus, and well, not more, but we have both H plus and BH plus in my solution. So of course the H plus takes over after a certain region. And my pH is minus log of H3O plus, which is in excess amount. Now, how do you know these concentrations? It's best to put them on a chart, and we're gonna see that when we do the problem solving set. Okay, so let's look again at some of the indicators here that we can use. Again, if we have this region of indicator here, look here. So this is where my pH change is my equivalence point is taking place. And of course, my equivalence point is less than 7 because I have an acid being produced at my equivalence. And what can I use here? Actually here, I'm allowed to use the methyl red, but phenolphthalein is not in the region where it's actually more in the buffer region, and a better curve maybe would be this. Here, again, methyl red can be used because it's within the pH change and of the equivalence point, but phenolphthalein is not in this volume at around 40. It's not within that range. Cannot be used. And great, so we're gonna do the triprotics in my next recording. So please, your homework is number 48 and number 49. And right away, go and do them and check out my solutions for those two problems.